Imagine stepping into a room that is just completely silent. Not just quiet, but a silence that feels heavy.
Like a physical presence.
Exactly. It's this cocoon of polished stainless steel, and it's engineered to kill every single vibration, every stray bit of energy.
And when we say cold, we're not talking winter cold. We're talking about the millikelvin regime. It's this tiny, tiny sliver on the thermometer, just a breath away from absolute zero.
It's colder than deep space.
Fundamentally colder and quieter than the void between galaxies. And it's all happening in a lab right here on Earth.
And right in the middle of all that cold and all that silence, you find this tiny little thing, a loop of metal etched with incredible precision.
And it's broken by this almost impossibly thin layer of insulator. That whole component is called a Josephson Junction.
Now, what's so wild is that this isn't an atom. You can see it with a regular microscope.
Oh, yeah. It's huge by atomic standards. It's made of billions upon billions of atoms, maybe, 10 to the 17 of them, all working together. It is, by any normal definition, a macroscopic object. A big thing.
And this is where the whole paradox comes in, the one they were trying to solve. For decades, we've had this idea, this sort of philosophical nightmare of Schrödinger's cat.
Right. The cat that's somehow alive and dead at the same time.
And we always said, okay, that's absurd. That's a thought experiment for the atomic world. It doesn't apply to, a cat.
The standard thinking was that anything big, anything you could actually see, would have its quantum weirdness instantly destroyed. The classical world is just too messy and warm for that stuff to survive.
But the question that John Clarke, Michel Devoret, and John Martinis asked was, well, it was kind of audacious. They asked, what if that line between the quantum and the classical world isn't a fixed wall?
What if we could engineer a big system, a macroscopic system, to be so clean, so perfectly isolated that it had no choice but to follow quantum rules?
They weren't looking for a cat that was half alive. They were looking for an electrical current in that visible circuit that was flowing clockwise and counterclockwise.
At the exact same time.
And they proved it could happen. Their work showed macroscopic quantum tunneling and energy quantization in a real piece of hardware you can build.
And that work, that turned quantum theory from blackboard equations into the actual foundation of quantum computing.
Which is exactly why they got the 2025 Nobel Prize in Physics. So our mission today is to unpack how they did it, how they forced the rules of the small world onto the big world.
And in doing so, basically created the whole field of quantum engineering.
Okay, let's get into it. To really get how bold this experiment was, we have to talk about the wall they were trying to break through. This wall of classical reality.
For decades, it was just accepted that there are these two core quantum ideas that just couldn't survive in something as big as a circuit.
These were the villain's main weapons, right?
Yeah.
Things keeping the quantum world locked away.
Exactly.
So the first one is energy quantization. We use the analogy of a ramp versus a ladder. Classically, energy is a ramp. A current in a circuit can be 1 volt or 1.001 volts.
Any value. It's continuous. You can stop anywhere on the ramp.
But in the quantum world, energy is a ladder. It's discrete.
Yeah.
It only comes in these specific little packets called quanta.
Right. An electron in an atom can be on the first rung or the second rung, but it physically cannot exist in the space between the rungs.
And trying to apply that to a huge electrical circuit just sounded, well, ridiculous. How could this thing made of 10 to the 17 atoms be stuck with only a few specific energy states?
It just seemed impossible. Which brings us to the second, even weirder idea, quantum tunneling.
Okay, classically, this is simple. If I throw a baseball at a wall, it bounces back. It can't go through unless it has enough energy to break the wall.
Energy is conserved. You have to have enough energy to get over the barrier.
But tunneling is the quantum world just ignoring that rule.
Kind of. The particle doesn't have enough energy to go over the barrier, but it still has this small but very real probability of just appearing on the other side.
It just tunnels straight through.
It's not really breaking the law. It's just that at that scale, particles are also waves, and their location is all about probability. There's a tiny probability it's on the other side, so sometimes it is.
So wait, stop here for a second. If these rules are so fundamental, why was everyone so sure they wouldn't apply to a bigger circuit? Why was the answer always no to macroscopic tunneling?
It all comes down to one big villain, decoherence. Or, more simply, noise and heat.
Okay.
The idea is that quantum states, like the clockwise and counterclockwise at the same time state, are just unbelievably delicate.
So a little bit of heat comes in.
A single stray photon, a random vibration, a tiny fluctuation in a nearby electric field.
Huh.
Any of that stuff, what we call noise, touches the system and poof,
The superposition is gone.
instantly.
Yeah.
It forces the system to choose a classical state, either clockwise or counterclockwise, not both. And the bigger your system, the more atoms it has, the more ways it can be touched by the outside world.
So it just gets messy and the quantum magic disappears.
That's why the classical wall seems so solid. The environment itself was the guard.
Okay, so to fight this villain, they focused all their attention on one component, the Josephson Junction, or JJ. Let's break down what that is.
So at its heart, a JJ is really simple. It's two pieces of superconductor with a very, very thin slice of insulator between them, like an oxide layer.
And when you cool it way down, it becomes a superconductor. The current is carried by these things called Cooper pairs.
Right. Pairs of electrons that bind together and start acting like one single giant quantum wave. And the magic of the JJ is that these Cooper pairs can actually tunnel through that insulating barrier without any voltage. That's the Josephson effect.
And the amount of current that flows depends on the quantum phase difference between the two sides. That phase became the thing they needed to track.
And to understand how that phase behaves, they use something called the RCSJ model. And that model gives us this incredible visual analogy for what's happening.
With washboard potential.
Well, washboard potential. It's the key to understanding this whole thing.
So let's really picture this. We've got a metal washboard, the kind with ripples, and it's tilted at an angle. The quantum phase of the current is like a tiny little ball sitting on that washboard.
Exactly. The dips in the washboard, the little wells, are stable states for the junction. When the ball is sitting in one of those wells, there's zero voltage across the junction. That's the state you want.
And the external current we apply, the bias current, is what tilts the washboard.
The more current you push through, the steeper the tilt.
Hmm.
And that makes the wells on the uphill side shallower. It's trying to force the ball to escape.
So if the ball escapes the well, say it rolls over the little hump into the next dip.
That's the switch. The junction instantly flips to a normal voltage-carrying state. And you can measure that voltage spike. That's your signal. That's the escape event.
Okay, so the whole experiment is about watching this ball escape from its little trap. And theory said it could happen in two totally different ways.
The first way is the boring classical way. It's called thermal activation.
This is basically just heat, right? The system is warm, so the washboard is shaking.
Exactly. The shaking jostles the ball around until it randomly gets enough of a kick to roll over the top of the hill. The warmer it is, the more it shakes, the more often it escapes. Simple.
And if you cool it down, the shaking should stop and the ball should stay put.
That was the classical prediction. But the controversial prediction, the quantum one, was macroscopic quantum tunneling.
MQT.
And MQT said that even if you cool it to absolute zero, so the shaking completely stops.
The ball, this macroscopic phase particle representing billions of electrons, should still have a small chance of just tunneling through the wall of the well instead of rolling over it.
So the whole bet was this. If they could cool the circuit down to almost nothing, and the ball still kept escaping at some constant minimum rate,
Then they would have proved MQT. They would have proved that quantum mechanics was in charge of this big engineered object. So the challenge was just immense. This wasn't just a clever idea. It was a brutal engineering problem. They had to defeat that noise villain by building the quietest place on Earth.
the first step, phase one, was non-negotiable. Extreme cold,
Colder than space.
millikelvin temperatures. To do that, you need these huge, complex machines called dilution refrigerators. They use different isotopes of helium to pull every last bit of heat out of the system.
The whole point is to stop that classical escape, thermal shaping.
Right, you're trying to make the washboard perfectly still, so the only way out is the quantum way.
But it's not just heat, right? You said there's other noise.
Oh yeah, that's where the real genius came in. They built layers and layers of shielding, metal to block stray magnetic fields. They put the whole thing on these special platforms to damp out any physical vibrations.
Like trying to perform surgery on a boat in a storm.
Exactly.
Yeah.
And the wiring itself had to be heavily filtered to stop any electronic noise from the outside world from getting into the circuit. They were literally building a fortress for a quantum state.
And all this leads up to the actual measurement, phase two. They're just sitting there waiting for the circuit to spontaneously switch.
Yep. They were measuring the escape rate. How often does that ball jump out of the well? And to get good data, you have to do it thousands and thousands of times.
Just run the experiment over and over to build up the statistics.
And here's the part of the method that made it so So definitive, so undeniable. Before they even tried to look for the quantum effect, they measured everything about the junction in the classical regime.
Wait, what do you mean? They measured it while it was still warm?
Exactly. While it was still warm enough for thermal activation to be the only game in town,
Yeah.
they measured its capacitance, its resistance, all the classical properties.
Why is that so important? It feels like you should be measuring it when it's cold.
Because those classical numbers define the exact shape of the washboard potential for that specific chip. They tell you exactly how deep the wells are and how thick the barriers are.
Ah, okay, so they're mapping out the landscape.
They're mapping the landscape. And then they could take those measured numbers and plug them in to the quantum MQT theory. And that theory would spit out a single precise number, a prediction with no wiggle room.
So it wasn't just, hey, we see a rate that looks kind of like the theory.
No, it was, based on the classical properties of this exact circuit, quantum mechanics predicts the tunneling rate at 0 temperature must be X. No adjustable parameters, no fudging, it must be X.
And then they cooled it down to see if they got X.
That's what made it bulletproof.
Okay, let's use the analogy engine. Let's make this Jell-O thing really concrete.
The Jell-O in the egg carton, I like it.
So the egg carton is our washboard potential. The Jell-O in one of the cups is our quantum state. We tilt the carton, that's the bias current. Now, thermal activation, the classical escape, is like being in a warm room. The Jell-O is wobbly, it's sloshing around.
Right, the heat is shaking it. And eventually, just by chance, a big enough slosh happens, and some of the Jell-O spills over the little plastic divider into the next cup.
The warmer the room, the faster it sloshes, the sooner it escapes.
Perfect. Now, for MQT, you drop the temperature to absolute 0. The Jell-O freezes solid. There's no more sloshing. It's perfectly still.
But the carton is still tilted, so the frozen block of Jell-O is pressing against the divider.
And the prediction of macroscopic quantum tunneling is that the solid frozen Jell-O will just reappear on the other side of the plastic wall.
Without melting, without going over the top.
It just tunnels through. The probability of that happening is built into the quantum rules of the Jell-O itself. It has nothing to do with the temperature of the room.
And this is where the really big idea clicks into place. By trapping that Jell-O, they realized they hadn't just observed a weird effect, they had built something.
They had built a controllable quantum system. They realized that the different energy states the ball could have while trapped in that well, they weren't continuous, they were discrete.
Like the rungs on the ladder.
Just like the rungs on the ladder in a natural atom. And that was the birth of the artificial atom.
So instead of being stuck with whatever atoms nature gives you, you can now design and build your own atom on a chip.
An atom where you can control the spacing between the energy levels just by changing the circuit. That's not physics anymore. That's quantum engineering.
So after all that insane engineering, the moment of truth finally arrives. They start cooling the system down, measuring that escape rate every step of the way.
And at first, everything behaved exactly as you'd expect. Perfectly classical.
As it got colder, the rate of escape dropped. The shaking was dying down, so the ball wasn't rolling over the hill as often.
Right, it was this perfect exponential decay, exactly what the thermal activation model predicted. They were confirming the easy part. They were proving they had successfully quieted the environment.
But then they hit the crossover temperature.
Below a certain point, the data just broke away from the classical prediction. Instead of continuing to drop towards 0, the escape rate just flattened out. It hit a floor.
It just stopped changing. It didn't matter if they made it a little colder or a lot colder. The rate was stuck.
It was stubbornly, beautifully constant.
And that constant rate.
That constant temperature-independent rate was the smoking gun. It perfectly matched that single pre-calculated 0 fudge factor prediction for macroscopic quantum tunneling.
So the ball was no longer being shaken out, it was tunneling out.
It proved, without a doubt, that the collective state of billions of electrons in that circuit was obeying the bizarre probabilistic rules of quantum mechanics.
And it wasn't just the rate. You said they actually measured the energy levels inside the well.
Yes, and that's a critical point the sources make. They were able to perform spectroscopy on the system and directly observe the quantized energy levels. They saw the rungs of the ladder. It proved the artificial atom wasn't just an analogy, it was real.
And if you have discrete energy levels, you have the building blocks of a computer.
That's the moment. The lowest energy level, the ground state, can be your quantum bit 0.
And the next level up, the first excited state, is your quantum bit 1.
And the artificial atom they built. That's what we now call a superconducting qubit.
Okay, so this discovery opens a door. But the next challenge is actually walking through it. Proving MQT is one thing, but making a useful qubit is another. The noise villain is still out there, right?
Exactly. The game shifted immediately from, can we see a quantum effect, to, can we protect this quantum effect long enough to do something with it?
And when we talk about protecting it, we're talking about something called coherence time. Can you break that down for us?
Sure. Coherence time basically has two main flavors. The first is called T1, the energy relaxation time.
Okay.
That's just how long it takes for a qubit in the excited state, the one state, to spontaneously decay back down to the ground state, the zero state. It's basically the qubit forgetting its energy.
And the other one
Is T2, the dephasing time.
Yeah.
This is the more subtle one, is how long the qubit can maintain a superposition. That magical both 0 and 1 at the same time state before environmental noise messes up the phase relationship between them.
So T2 is how long the quantum magic lasts.
You got it. And for a long time, T2 was way, way shorter than T1, which meant noise was killing the magic long before the energy even had a chance to decay.
So the whole engineering quest became about making T1 and T2 as long as possible.
Precisely. And that quest starts with one of the first real engineered qubits, Devoret's quantronium.
What was the big innovation there?
The innovation wasn't so much a new structure, but a new way of operating it. They figured out that there was a special sweet spot you could tune the qubit to, a place called the charge degeneracy point.
That sweet spot.
Yeah, it's a point where the qubit's energy levels become, for a moment, almost totally insensitive to the main source of noise at the time, which was charge, noise, random fluctuations of background charge.
So they found the quietest corner in a very noisy room.
That's a perfect analogy. And just by operating it there, they immediately boosted the dephasing times by a factor of 10, sometimes even 100. It was a huge leap.
But it was still pretty sensitive if you weren't right on that magic spot.
Exactly. Which led to the next big evolution, the one that really dominates today, the Transmon Qubit.
The Transmon, this is the workhorse. What did they change to make it so much better?
The big idea was to add a giant capacitor in parallel with the Josephson Junction.
What does that do?
What it does is it dramatically changes the ratio of two key energies in the system. It makes the Josephson energy, EJ, much, much larger than the charging energy, EC.
And making that ratio big.
It has the effect of flattening out the energy bands. It makes the energy difference between the 0 and 1 states almost completely immune to that charge noise that plagued the quantronium.
So instead of finding a tiny quiet spot, they basically engineered the qubit to be wearing noise-canceling headphones.
That's it. It's just deaf to the charge noise. That innovation made the qubits way more stable and much easier to build and control, which is what allowed people to start scaling up to multiple qubits.
And then even later, we get designs like the fluxonium.
Right. The fluxonium is designed to be immune to a different kind of noise, flux noise, which is fluctuations in magnetic fields. It does this by adding a big inductor, which is cleverly made out of a whole array of smaller JJs.
So it's like a different kind of armor for a different kind of attack.
Exactly. The whole story of qubit development, from quantronium to transmon to fluxonium, is this constant, clever arms race against environmental noise. It all started with that first MQT experiment, proving it was even possible to have a quantum state to protect.
The moment they confirmed MQT, it was like a starting pistol went off for a whole new kind of tech race.
It really was. People call it Moore's Law for quantum coherence. Instead of doubling the number of transistors on a chip, the goal became to exponentially increase how long a qubit could stay coherent.
And the numbers are just staggering. You said 5 orders of magnitude?
Yeah, I mean, we went from coherence times measured in nanoseconds, billionths of a second, to now, where we see well over 100 microseconds in the best systems.
That's a million-fold improvement.
A millionfold. That leap in stability is what made everything else possible. You can't run a complex quantum algorithm if your qubits forget what they're doing before you're even finished.
And this journey, this race, led directly to John Martinis, one of the original MQT pioneers, leading the Google team to that huge milestone in 2019.
Quantum supremacy.
Quantum supremacy. Now, that's a big, flashy term. What did their Sycamore chip actually do?
The Sycamore processor had 53 of these superconducting qubits, direct descendants of that first artificial atom. And they gave it a very specific, very hard problem to solve.
Which was?
It's called random circuit sampling. Basically, they run a chaotic sequence of operations on all the qubits. The task is to predict the most likely outcomes.
And why is that so hard for a normal computer?
Because to simulate 53 qubits, A classical computer has to keep track of 2 to the power of 53 different possibilities at the same time. That number is just astronomically huge. The memory and processing power required grows exponentially.
It's just an impossible calculation.
For a classical machine, yes. They estimated that the world's most powerful supercomputer at the time, Summit, would have taken about 10,000 years to do the same calculation.
And Sycamore did it in
200 seconds.
10,000 years versus 200 seconds.
That's the power of quantum computation. And it was the ultimate proof that this journey, which started with a tiny ball tunneling out of a well, had fundamentally changed what was computationally possible.
But what's fascinating is that this legacy goes way beyond just building computers. It also completely changed our ability to measure things.
Yes, quantum sensing. This is a huge, often overlooked part of the story. That same Josephson Junction is the heart of the most sensitive magnetic field detectors ever created.
Squeeds, superconducting quantum interference devices.
Exactly. Squeeds work because the magnetic flux, the magnetic field passing through a superconducting loop, is quantized. It can only exist in discrete packets.
So a tiny, tiny change in the external magnetic field causes a detectable change in the squid's current.
A precisely measurable change. They are so sensitive, they can measure fields in the femtotesla range.
What does that even mean in the real world?
It means we can measure the magnetic fields generated by neurons firing in your brain.
You're kidding.
Not at all. We use arrays of quides to do magnetoencephalography or MEG scans. We are literally using a device based on MQT to map the electrical activity of human thought.
That is just mind-blowing. A quantum effect that was supposed to be too fragile for the big world is now being used to study the human brain.
And it doesn't stop there. They're also used as single photon detectors.
How does that work?
It's the same switching principle. A single photon of light, say from a microwave source, can hit the superconductor and have just enough energy to break a Cooper pair.
And breaking that pair
Breaks the whole superconducting state. The junction instantly switches to its resistive voltage carrying state. So a single particle of light triggers a macroscopic electrical signal.
So you can count individual photons.
With incredible precision, which is essential for things like quantum cryptography and even searching for dark matter.
So to wrap this whole deep dive up, the biggest takeaway seems to be philosophical. We used to have these two sets of rules for the universe.
Newton for the big stuff, quantum mechanics for the tiny stuff. 2 different worlds.
And what Clarke, Devoret, and Martinis showed is that there's no hard line. That separation isn't real.
It's not a fundamental division. It's just a matter of engineering and isolation.
If you can build a system that's clean enough, quiet enough, and cold enough, quantum mechanics will happily take over no matter how big the system is.
They proved that the classical world is just what a quantum system looks like when it's noisy. They built a bridge over that divide and showed us we could walk across it.
The journey from that one weird beta point, a constant escape rate at the bottom of a graph, to a 53-qubit processor that outpaces all of classical computing is just one of the greatest science adventures of our time.
And it feels like we're still just at the very beginning of what these artificial quantum systems can do.
So we'll leave you with this to think about on your own. If we can engineer a circuit with billions of atoms to behave as a single coherent quantum object, where does it stop? What are the real limits? Could we, one day, isolate something even more complex, maybe even a biological system, well enough to see the quantum rules hiding just beneath the surface of our classical world?
Maybe the classical world is just a quantum system we haven't figured out how to isolate yet.
A profound thought. Thanks for joining us on this deep dive into the very beginnings of the quantum age.